Okay, so first of all, your midterm grades have been announced. You have probably seen it on the class. You will be able to see your papers probably on Friday afternoon. I will just send you an email about the date and the place. Now, there were a few common mistakes in the midterm. Before starting the lecture, I would like to go over some of them. Okay, so one of the mistakes was in question 3. If you remember, we had these 3 charges, plus Q, minus 2Q, and plus Q located in this form. This was your X and the Y axis. In one of the parts, you were asked to calculate the electric field at this point A. Okay, you did calculate it, and you found that at least the electric field was some coefficient times Q over A squared in some direction. Okay, this was the answer. The answer is not this. The answer is Q over A squared A E. Now, this is not the answer. Okay, that is one thing. You have to learn how to write the vectors in their proper form. You cannot just show it like this, unless you are explicitly asked to show it. Anyway, this is not the common mistake. Another mistake was, once you obtain this electric field, the next part asks you to calculate the potential at the point A. Well, you can calculate the potential at the point A just by summing the potentials created by all these 3 charges. That is one way of calculating. Or you could have some of you tried to calculate this integral, E dot dl. Now, if you want to calculate this integral, first of all, you have to choose one path. What is your path? You cannot just say that you cannot just evaluate this integral just like as if it was just a one-dimensional integral. And without specifying a path, you cannot calculate this one. Well, most of you just ignore to specify paths. Well, in the exam, it was mainly simple integrals, so the result turns out to be correct, but what you did was wrong. Anyway, so some of you just, okay, so this was the definition, and then you said, okay, this is equal to Q over L squared dl. Now, this is seriously wrong. In this particular example, it just introduces a sign mistake. But in general, it's a serious error in the sense that if you look at this expression, E dot dl. Now, this is how we define the, let's say, potential difference from point P1 to point P2. Okay, one thing is, how does one evaluate such line integrals? I mean, in the exam, I'm not asking you to evaluate such line integrals if they are not trivial. But nevertheless, you do need to understand what these symbols mean. Now, in here, okay, the explanation of this symbol is you just take a path connecting P1 to P2. If this is your P1, this is your P2. In the case of the potential difference, you can choose any path that you like, but nevertheless, you still have to choose one path to evaluate the integral. Then you divide this path into small segments. Each one of these segments, let's say, you have to consider a sum over all these very small segments. And if you denote each segment by dl, E is the electric field on this segment. It's not an arbitrary electric field, it is the electric field on this segment. And then you have the dl for this segment. You do this calculation for all of these segments. You calculate the electric field on this segment, multiply it by dl on that segment, and sum them up. Now, the mistake over here is, you see, this expression for the electric field is valid only for this point over here. It is not valid for any other point along the path. It will have a different expression. So if you just put this electric field in this integral, it is wrong. Well, in this case, the only error is, I think it's I mean, you don't even get an error, you get the correct answer, but it's just by luck. It's just by chance. Now, this was a common mistake. Now, another common mistake was in question 4, which, I mean, you were given the, okay, you had these infinite plates. And then, okay, in part A, for A, you were supposed to calculate the electric field using Gauss's law. Now, this was one of the questions where you had this problem of memorizing formulas. I mean, apparently you are also even trying to memorize the steps in solutions to certain problems. In the sense that there were quite a number of students who remembered that for such a circle, such a plate, you need to take a cylinder, but you just couldn't remember how to put the cylinder. I mean, some of you just put the cylinders just like this. Okay, this was one of the cylinders. Another group of students took such a cylinder, and okay, and another thing was, although you took such cylinders, your result was correct. Oh, there was also another group which took cylinders like this. Okay, even those who just assumed small cylinders, okay, the question was asking you, why do you choose that Gauss surface? And of course, you remember the magic word, due to the symmetry. But what does that mean? So how do you start from that symmetry and arrive at the conclusion that you have to choose a cylinder? I think there were only 1 or 2 students who actually explained all these steps. That's one of the places where most of you lost lots of points. Okay, in most of the questions, you do take partial credit for the things that you have done. But for certain types of mistakes, I don't give partial credit. And those kind of mistakes is, for example, if you find that 1 kilogram of proton, 1 kilogram of carbon, let's say, contains 10 to the power minus 25 protons, then that's a serious mistake. I mean, that's a mistake that doesn't even deserve a partial credit. You have to look at your answer and think whether your answer makes sense or not. If you find that 1 kilogram of carbon doesn't even contain 1 proton, that's a serious problem. The same thing holds if you find, let's say, 100,000 protons. Again, that's a serious problem. You already have this concept of Avogadro's number, and typically around 10 grams of material contains of the order of an Avogadro's number of protons. So you should be able to know those numbers. I mean, in higher schools, we have examples where the students estimate the size of a hydrogen atom to be of several kilometers. I mean, these mistakes are not acceptable. I mean, you do some mistakes all the time. Everybody does mistakes. You forget a sign over here, another over there. Instead of dividing, you multiply. But you have to look at your answer. What does your answer mean? Any questions on this? Or any questions? Okay, back to our lecture subject. Any questions on what we have done last week or the previous weeks before we continue? Last week we started studying the forces due to this field that we invented that we call the magnetic field. Okay, it was first observed that there was this new force which we couldn't explain in terms of electrostatic forces, and furthermore, it had this weird property that the force that an object feels at this point changed whether it was depending on in which direction it was moving. So if we had some charged particle moving in one direction, it felt one kind of force. If it moved in the other direction, it felt a different force, although it was passing through the same point. Now, this doesn't happen in the electric field. In the case of the electric field, the direction of the force, electric force, is determined by the direction of the electric field only. It doesn't depend on the velocity. But this new force has this weird property that its direction also depends on the velocity. And we had also seen that in general, if you have any object, any charged object in a region where we have electric and magnetic fields, it will feel such a force Q E plus V cross B. And we also studied what kind of a force acts on a current carrying wire. And that was basically it. Now, any questions on these? Or how to determine the directions of these forces? We also studied the magnetic dipoles. A current carrying loop has this magnetic dipole. And if you put a magnetic dipole inside a magnetic field, it will create some torque. It will feel some torque. And in fact, this is what is used in building electric motors. Inside the electric motors, you have the coils. And when you pass some current through it, it will become a magnetic dipole in a magnetic field, and hence it feels this torque and starts to rotate. Okay, then let's just discuss another phenomena that we will call the Hall effect. And then we will close this chapter. Now let's just imagine that we have a very thin conductor. Not necessarily small, but a thin one. This is our conductor. And let's assume that we connect it to a current. And let's furthermore assume that we put it in a uniform magnetic field. So there's a magnetic field. We take this, put it in a magnetic field, and let that current flow. Now, what are the charge carriers? What is this current made of? Yeah. A metal, let's say, an ordinary metal. The electrons will be moving. So we have an electron here. It will be drifting in this direction. What will be the direction of the force? Up or down? I heard some down. Up. You see, we have this, the velocity is in this direction, the magnetic field is towards the inside the screen, so V cross T is downward. But you see there's Q over there. The charge of the electron is negative. So this vector, there's no electric field yet. V cross P is pointing downwards. We multiply a vector pointing downward with a negative number, then it becomes a vector pointing upward. So the force that the electron will feel will be pointing upwards. So as the electrons are drifting from right to left, they will feel a force which pushes them upward. So we will have eventually, as a result, more electrons on the top than electrons on the bottom. So as the current is running through, usually when you have a wire, the wire is neutral everywhere. But if you put it in a magnetic field like this, it will just be the electrons are forced upwards, and hence there's the upper side of this becomes negatively charged. And the lower part becomes positively charged. And hence, if you put this strip in a magnetic field, there is a potential difference between these two sides. The upper side and the lower side has a potential difference. Now, which side will be at a higher potential? Well, the charge side will be at a higher potential. And if you just connect this to a voltmeter, and you will read a non-zero potential difference, which is called the Hall potential. Now let's see, what is this Hall potential? Let's try to calculate it. Now the electrons, well, if the charges accumulate on the sides, they will be creating an electric field. Before we only have an external magnetic field, but now this accumulation of charges on the top side will create an electric field inside our conductor. And it will be pointing in which direction? It will be upward from the positive to the negative. So this is the direction of the electric field that will build up. Now this is the magnetic force that this charge feels due to the external magnetic field. And what will be the direction of the electric field that this charge feels? The electric field is pointing upward. This is pointing upward now. The Q is negative, so the force due to this electric field will be pointing downward. So now we have this additional electric force acting on the electrons. Now, of course, if the magnetic field is larger than the electric field, there will be more electrons accumulating on the top part. Electrons will keep moving towards the up if the magnetic field is larger than the electric field, but that means there is more charge accumulates on the top side than on the bottom side, so the electric field becomes stronger. And the electric field keeps getting stronger as long as the magnetic field is larger than the electric field. Magnetic force is larger than the electric force. But eventually, the magnetic field is constant, so the magnetic force is constant. It is not changing. So eventually, the electric force will be equal to the magnetic force, and then the electrons, after that point, will just keep moving straight. And that will happen when the electric field plus V cross P is equal to 0. You see, the electric field, B is constant. Drift velocity is constant, more or less constant. But the electric field keeps increasing. So eventually this point will be reached. And when this is reached, the electrons will just go straight. There will be no longer accumulation of charges anywhere. Now, of course, this means that E should be equal to V times P. You see, E is pointing upward, V cross P is pointing downward. The magnitude of V cross P is V times P. The magnitude of E, let's say, is just E. So they cancel if this is satisfied. So we know the electric field. If we know the drift velocity. When the equilibrium is reached, of course. Now, if you assume that the length is, let's say, just D, the potential difference, well, it's a region where the electric field is more or less uniform. It has this value everywhere. And so the potential difference is nothing but the electric field times D. This is constant electric field, which is ED, which is drift velocity, the magnetic field times the width. Which one? Q times? No. This V is velocity, by the way, it's not the potential. But QV cross P. No, I mean, you can just open this up. This is equal to QE plus QV cross B. Before we had only written this one. But if there is also electric field, there is also this electric force. Well, I mean, it doesn't matter. It's the same thing. You can do it like that also. It doesn't change. No, I didn't understand the question. Can you repeat it? No, it is thin but wide. Well, it doesn't have to be thin, but if it is thick, then the magnetic field inside the metal will behave differently. Yeah, that's fine. You should be able to measure it yourself in the lab. You have the necessary sufficient equipment. Just pick up a voltmeter, just pick up one piece of aluminum foil, take some magnets. Magnets are cheap now. You can have a magnet which has a large magnetic field and see if you can measure this whole potential. It is short. It doesn't take long. The resistance. Well, you see, how did we define the resistance? We define the potential difference is I times R. Well, usually when you are defining such a potential difference, you are talking about the potential difference between these 2 points. You have that potential difference, there is a current running through it. If there is a current running through it, there will be a potential difference between these 2 points, and the proportionality constant is your resistance. Now, if there is a current running through it, we have just seen that there is a potential difference between these 2 points also. It's not along the direction of the flow of the current, but it's in the vertical direction, vertical to that direction. Well, that is called the Hall resistance also. But I mean, the resistance in this system, I mean, things do get complicated. Now, for the horizontal, it doesn't really have a significant influence on that. Unless, of course, you are at very low temperatures. Now, you see, there is, at some part, the electrons are accumulated over there. It takes a very short time. After that time, there's no electrons over there. The electrons just go straight. So it will not have any effect in that sense. I mean, the effect will be very small. Now, you see, in the absence of magnetic field, there are charges running through it. Unless you have a capacitor, the wires will be neutral. Your conductors will be neutral. They will not have any excess charge anywhere. Now, we take this system and put it in a magnetic field. We know that the magnetic field exerts forces on moving charges. So if you take an ordinary conductor, there will be when you run a current through it, there will be electrons moving. If the electrons are moving and you are exerting a magnetic field, the electrons will be pushed upwards by this magnetic force. So it's the magnetic force which is pushing the electrons upward, and hence creating a potential difference which we call the Hall potential. And this Hall potential is proportional to the magnetic field itself, the drift velocity, and the geometry of your sample. So you had this question, what is the drift velocity? How can we measure it? Well, you see a measurement of it. Just prepare this sample, apply a magnetic field to it, then you measure the whole potential. The drift velocity is this expression over here. So this is what you can measure, this is what you create, this is what you can measure just by the side geometry of your sample, and you have the drift velocity. Now, any questions on this one? Yes. No. It is when you measure, when you do this experiment at a very low temperature, at a very high magnetic field, it comes from there. I mean, then the phenomenon is completely different. You have the same setup, but completely different dynamics. Other questions? And by the way, by this measurement at very low temperatures and at a very high magnetic field, they got a Nobel Prize. Now, this problem is a Nobel Prize winning problem. Of course, it's the analog at very low temperatures and at very high magnetic fields. Because then there are new physics enter into the game, the phenomena changes drastically. No, it probably is not that. I mean, he's still alive. Okay, let's do a different example. Now, here we just took some ordinary metal. We said that, okay, it's the electrons that are carrying the charges. Let's imagine some different conductor. And let's assume that in this hypothetical conductor, this different conductor, the charge is carried by positive charges. So again, we have this magnetic field. But this time it is the positive charges that are drifting. Now, what will be the force that this positive charge will feel? What's this direction? Downward or up? Don't just say that it is in the opposite direction. It is not. It is pointing upward. You see, V is in the opposite direction now. Charge is of the opposite sign. So the force is still pointing upward. Or you can just say, this is the direction of the velocity. The magnetic field is inside the screen. V cross P, the force is upward. The charge is positive, so it doesn't change its direction. So the positive charges, they just accumulate on the top. And so the other part will be negatively charged. Now, if you just compare these two, if you measure the potential difference between the top part and the bottom part, in this case, if it is the potential that you measure is positive, in this case, it will be negative. Because in this case, it is the lower plate, lower side that is at a higher potential. In this one, it is the upper side that is at a higher potential. So by measuring the sign of this whole potential, you can determine whether the charge is carried by negative charges or positive charges. That's also another thing that you can determine about your material by just doing this experiment. Well, for the first case, what is the direction of V cross P? What is the charge of the electron? So a minus times a vector just flips its direction. So the force is pointing upward. In the bottom case, V cross B is already pointing upward. It's a positive charge, so the force is upward. Other questions? Yeah, this is your electric field. You are given 2 points. What's the potential difference between those 2 points? And as all the quizzes, you should do it on your own. And don't forget your units.